nanohub.org.
Online simulation and more for nanotechnology.
All right, guys, let's get started. Today we're going to continue talking about Monte Carlo. And we're going to formulate and solve with Monte Carlo yet one more uncertain propagation problem. Actually, I have written all these things down, so I'll just go over it. So the first thing that I'm going to show you is that Monte Carlo sometimes fails when you have a very problematic, let's say, when you have a problematic thing to calculate, like the probability of a rare event, the probability of something that doesn't occur very frequently. Okay, when you have something like that computed, then it's not working every single time, and you have to use your judgment a little bit to figure out if something works or not. We'll come up with one way to alleviate these challenges. It's called importance sampling, so I'll show you how importance sampling works. And then we'll introduce an extension, let's say, of Monte Carlo. So it's still going to be Monte Carlo, but instead of sampling random numbers, we're going to sample a special kind of random numbers that have better properties, at least if the dimensionality does not get very large. And this special kind of random sample is going to be called a Latin hypercube design. And then we'll formulate and solve an uncertain propagation problem, which is basically an initial value problem, a differential equation with uncertain initial conditions. All right. So, importance sampling is basically another way of calculating expectations of a function of a random variable. And I'll show you how it works. Okay, so the idea is to introduce another probability density Q of x instead of the probability density P of x that you had before, and express the expectation as an expectation of Q of x instead of the original one. So this may be a little bit hard to follow, but it's actually trivial. So you see, this is the expectation that you want to calculate. It's an integral basically over P of x, and then you're just forcing in there Q of x. So you say, okay, divide by Q of x, multiply by Q of x, then you get the expectation of something with respect to Q of x. And you can see it like that. So you have basically transformed the problem that is take an expectation with respect to P to a problem where you take an expectation with respect to Q, but they have the same answer. Okay, and there's really nothing magical. You just multiply and divide with the same thing. Okay, so the result will not change. But it will turn out that by using this trick, you can actually accelerate the convergence of Monte Carlo. And in some cases where Monte Carlo totally fails, like the estimation of the probability of rare events, you can actually create a method that works. Okay, anyway, as soon as and this Q of x can literally be anything you like. Absolutely anything you like, as soon as it is not zero. Okay, you can't pick zero, obviously. You can pick anything you like that has the same support as P of x. Do we understand what support means? It is not zero wherever P of x is not zero. Okay, this is the only requirement. Q of x should be positive wherever P of x is positive. This is the only thing that, the only restriction on Q of x. Apart from that, it could literally be anything you like. Okay? Now, once you have picked that Q of x somehow, and you have recasted this expectation with respect to P to an expectation with respect to Q, then you can do Monte Carlo here. Right? So you can just take samples. Instead of taking samples from P, you take samples from Q. And you come up with a sampling average for this thing. Right? So this is the sampling average that you would do 1 over n sum of the samples evaluated at whatever you have inside the expectation. Okay? And this thing will converge to that thing. Okay, simply because they're equal. So they will converge to the same thing. This is pretty much it. That's importance sampling. Okay, and the power of importance sampling comes with this fact, the fact that this Q can be anything you like. But let me just show you an example from Casella. By the way, this book, Casella's book, I have, it is on the library, so I'm referring to it. You can find it on the library. Chapter 3 is what we're going through right now. Now, if you read it, it is a little bit more detailed than what I cover in class, but you should probably read it if you want to learn a little bit more details. Anyway, so this is where I get this example from. So imagine now that we have a random variable x that is a standard normal. Standard normal meaning Gaussian, mean 0, variance 1. And let's say that what you want to calculate is the probability that x is greater than 4.5. This is all, very simple thing. Give me the probability that x is greater than 4.5. Of course you can do this, this is an integral, right? What integral? It's the expectation of the indicator function over all x's. So that indicator function counts, as you sample x's, it counts 1 if x is greater than 4.5, otherwise it counts 0. So if you take the sampling average, you will calculate this probability. This is all. And of course, this probability you can find it analytically, or almost analytically, or with a numerical quadrature, because it is 1D, so it is actually trivial, okay, to do it with a quadrature rule. And it is very small. It is like 10 to the minus 3 or so, maybe even smaller than that. It's actually smaller than that. But anyway, let's do a Monte Carlo estimation of that probability and see what happens. So to do a Monte Carlo estimation, you sample x's from the standard normal independently, and then you build this approximator, right? 1 over n, the count of the count, and then you divide with n the number of times that the sample was greater than 4.5. That's all. Okay, this is what this says. All right, let's run this for like 10,000 times. All right, so let's just pick n to be equal to 10,000. If you pick n equal to 10,000, what happens is that you don't get a single x that is greater than 4.5. Okay, so your estimate for that probability is 0. And as a matter of fact, if you make it bigger, like make it 1 million, maybe you hit it once. Okay, and that's also the wrong estimate of this rare probability. You have to go to 10 million or 100 million samples to get an accurate estimate of the probability that x is greater than 4.5. Okay, so this is something that this is a standard problem with Monte Carlo estimates when you try to estimate weird things that for example, like rare probabilities of rare events. All right, and you should keep this in mind, because in engineering applications, these are the probabilities that you're interested in. The probability that a nuclear reactor melts. All right, you want it to be small, like 10 to the minus 9. If you do your simulations, you do 10,000 simulations. Each one takes a week, and not a single time it fails. Right, so you haven't found anything, obviously. So you need to do something else. So here's where importance sampling can help. And here's how it works. I mean, obviously, this is a very simple example. For more complicated rare events, we have to do something else, but we'll talk about that later. So the idea is to introduce an importance sampling distribution that will only look at the relevant space. Right? So here I introduce this distribution, which is basically an exponential distribution that starts at 4.5. Basically, it's an exponential that's truncated at 4.5. It's not going to give me any samples that are smaller than 4.5. Okay, this is why, how did I come up without 4.5? When this is the limit in the indicator function. Okay, the indicator function is 0 before 4.5, so there's nothing to to find there anyway, so just ignore this region completely. And just make it, you know, exponential times the indicator function, and I introduce this normalization constant there because this needs to be an actual probability density. So I'm going to have to find a normalization constant that makes this thing integrate to 1. So if you make this thing integrate to 1, you can find that the normalization constant should be this expression right here, okay? It's just doing the integral to find a constant that will make this integrate to 1. Okay, and now you can introduce this guy as the important sampling density. So instead of sampling from P, which is a standard normal, we're going to be sampling from this, and we're going to change, just to give you an idea of how it looks like. This is how the standard normal looks like. It's the blue line, okay? And you want the area below the blue curve from this point on. As you can see, it's very small, okay? You can't even see it. It's very small. So you want this area. And see what the important sampling distribution does. It says, forget about that area. Okay, forget about less than 4.5. Let's just concentrate here. Okay, let's just concentrate in the area where failure occurs. That's what it says. All right. This is the idea of important sampling. Use Q to concentrate, to focus where the important stuff happens. And so let's use now that Q to change this expectation from an expectation with respect to the standard normal to an expectation with respect to Q. And come up with a sampling average. So again, remember that this is an integral with respect to P of x, and you are dividing with Q of x and multiplying with Q of x, and you're turning it into an integral with respect to Q. So the sampling average approximation of this using Q as important sampling is as follows. You sample independently from Q, and you take the sampling average of this expression, okay, which we derived at the beginning. And of course, if you plug in the numbers, you're going to get this particular expression for this specific example. All right, so you're just going to average that. And for 10,000 samples now, you get something. Actually, this is extremely close to the actual probability. The error is in the 7th significant, it's in the, yes, 7th digit. And it's, the actual probability is 10 to the minus 6, right? 3.4 10 to the minus 6. So if you take 1,000,000 samples with the classic Monte Carlo, you will hopefully get 3 times a number that is greater than 4.5. But in order to actually estimate the 4.5, you will have to get perhaps hundreds of millions of samples. So it's next to impossible to do it without important sampling, this particular one. All right. I mean, I know that it doesn't look very fancy, but let's state the take-home message. If you want to compute the probability of a rare event, and let's define as a rare event anything that is expected to have a probability that is smaller than, let's say, 5%, right? Then you should probably not do Monte Carlo. You should think about it. You should think about the possibility of biasing your samples so that you force you force the random variables to cause failure in your system, or however whatever that rare event means to you. You should bias your sample so that this rare event happens. Okay, that's the whole point. And actually, there are advanced sampling techniques that that allow you to construct an important sampling distribution that is going to bias in the right way sequentially. Okay, but these are more advanced things, and you could do your project on one of these if what you have to do is calculate an error probability. Anyway, so take-home message, rare probability, you have to calculate a rare probability. Just don't use Monte Carlo blindly because you're going to get garbage, okay? You should really think about it. Probably Google it. Yes? What was that? So the support of Q has to be the intersection of the support of P, which is the original distribution, and the support of this, of the function you're integrating over. So Q has to, so if the function is 0, like this function is 0 before 4.5, then Q can completely ignore that region without any problem. It doesn't matter. Okay? So it is the support of F times P, if you like. Yes?
So, like in this case, when we are using the Q function, how will the variance be equal to the original function? Will it be the same? Will it change?
The variance of the estimator, you mean? The variance of the estimator will be completely, it is different. So each Monte Carlo estimator has its own variance. So this one has its own variance, the other one has its own variance, but if you notice, in the previous estimation where we didn't use importance sampling, right? The variance we got was 0, because we didn't even get a single one. So basically here, the central limit theorem that gives you the variance has not kicked in yet. And it would kick in when you had a few 100 million samples. That's when it would kick in. So this is utter garbage. Okay, and of course you should use your judgment. If what you're calculating is an extremely small quantity, that depends on something happening 1 out of 1,000,000 times, then you should probably be careful with it. Right? That's a take-home message. All right. Any other questions about that before I move to another interesting part? Another interesting problem of Monte Carlo? Yes?
It might be a silly question, but 4.5 is only applies for this example.
Yes. Yes. So, yeah. So, this is an extremely important question, actually. It's not silly. Q, the best Q, you can use any Q you want. And if you make a bad choice for Q, you may actually get a worse estimator than the one you just get with plain old Monte Carlo. Okay? You can actually make it worse. Chances are that you will make it worse if you just randomly pick a Q. And the best Q for your problem depends on both the underlying probability and whatever you're integrating here. And you need to use your judge. I can show you what is the optimal. I will tell you what is the optimal Q. There is an optimal Q. But most of the times finding the optimal Q is more difficult than evaluating this expectation. But it turns out that in many practical cases, you can use your judgment to come up with a good enough Q. So here we used our judgment to say, if this is the probability of failure, right? So if X corresponds to, let's say, the state of our system, and we know that if it goes above 4.5, we're going to have a failure, then it makes sense to construct Q so that it makes that happen more often, so that we can measure better that probability. That's how we built it. All right, so, and here's where you're gonna see the problem. So not all estimators are created equal, and you can pick that Q, and that Q can be anything you want, and you will probably make it worse if you don't think about the choice of that Q. But let's see what can happen. Now let's find the variance of that estimator. To find the variance of the estimator, we just apply the variance operator everywhere here, okay? And you are using so the 1/n will get out, this is a typo, should get a square. No, actually this is not a typo, it is 1/n, because these are all the same. And then for this guy, I use the standard formula for the variance, like the expectation of the square minus the square of the expectation. All right, so this is how the variance of this estimator looks like. And so you have these two terms. Now, if you are computing an expectation, hopefully that expectation is not infinite. So this term here is a finite number, okay? Otherwise, what are we talking about? Okay, the answer is infinity. So let's say that this is finite. So what you want from a good estimator is to minimize this part of the variance, make this as small as possible. And you can actually work out that the best Q is one that is proportional to F times P. You can work this out by using variational calculus. Take the functional derivative with respect to Q, set it equal to 0, and solve for Q. You will find that Q should be proportional to F times P. Okay, which makes sense. All right. But anyway, it is possible, if you don't really think about the choice of Q, that this variance here is infinite. Okay, it is entirely possible that this thing here is not a finite number. Then look at what happened. If this is infinite, then this thing will still converge to the right answer, but if you stop before infinity, you may get garbage. It's a little bit tricky, okay? So, if this variance is truly infinite, then you cannot really trust your Monte Carlo estimator. That's what I mean. Alright, so we must always have that the variance, the variance of the estimator is finite. And if it's not finite, then we cannot trust the results. Okay? And I'll show you what happens. I'll show you what happens right now. So I created an example where this fails, and you will see how strange of a Monte Carlo estimate we're going to get. So just to repeat it, this thing always converges to the truth. And the convergence, mathematically it's called, it is a convergence almost surely, okay? But it is, of course, a statement as n goes to infinity. It will converge. Now, the problem is that if the variance is not finite, then the central limit theorem does not hold. So if you stop prematurely, you cannot really bound your epistemic uncertainty. And then strange things can happen. Here's a ridiculous example. I probably spent like a day trying to come up with a simplest possible example for that. And that's the simplest I could come up with. So you take a random variable that comes from an exponential with rate 1. This is the density for that exponential, okay? And I'm going to integrate x. So I'm just going to take the expectation of x, which is of course 1. I know the answer. The answer is 1. And I'm going to introduce a stupid, really stupid importance sampling distribution. This one. This, if you look at it carefully, it is actually a truncated standard normal. Truncated at the negative number. So I'm just keeping the positive part of a standard normal. And then you integrate it, make sure you find the C that will make that integrate to 1. Okay? So now I'm gonna use this as a biasing distribution or as an importance sampling distribution to get the expectation of x. Okay, but look at what happens. If you look at this integral, right, which is the term that dominates the variance of the estimator, I can do it analytically. So I'll get this, and I'll get that, and I'll get infinity. Okay, so the variance of the estimator will be infinity. Because here, I mean, you have this term that tries to kill the exponential, but the square is going to win, and it's going to make it blow up. Okay, so this blows up. So here's what happens to the estimator. The truth is 1. Okay, so this is the true value. And if I run this estimator up to 100, you get something like that. And you say, okay, maybe 100 is a small number. Let's make it 1000. And you make it 1000. And then it looks like that. And you say, maybe 1000 is a small number. Let me make it 10,000. And you make it 10,000, you run from scratch, and it looks like that. And it looks as if, imagine that you don't know the red line, okay? The red line is unknown to you. And you're just looking at the blue thing, and you would say, okay, that's probably good enough. Let me stop taking samples. The estimate is 0.9, and you are 10% off, okay? Because if you run it even longer, it will change. And you run it for 10,000 samples. No, actually, this is 100,000 samples, and it still looks like it converges. But if you haven't seen the red line, but you are completely off, okay? And there's no cure for that. This is just because the estimator is complete garbage. This estimator, if you keep going forever, it will converge to the red line. But it's really forever. It's not 1 billion, it's forever. Even at 1 billion, you should not trust the result of this estimator. And here's how, it would look if you run it 10 different times. So the characteristic of this is an estimator with an infinite variance, and its characteristic is that it can jump without notice. So again, you see, if you do many samples, you will start seeing huge jumps. As a matter of fact, the more samples you do, the bigger the jump you're gonna get. So look at that part, right? So it was small, and then suddenly it jumped to 10, and then it was going down. And you can actually show mathematically that there's gonna be another jump sometime in the future that's still gonna be big. Anyway, it's just garbage, okay? So just forget about it. You don't want an estimator that has an infinite epistemic uncertainty, okay? All right. Any questions about that before I move to the next topic?
Yes.
Yeah.
On the graphs, at the first graphs, it was going from 0 to 1, right? Or before? Okay. So the scale on the y-axis, why does it change when you put them all together and goes up to 20?
Oh, because when I do this experiment from scratch, it starts at a random point, which could be very high. Right? I'm just letting the matplotlib to pick the scale. So it just happens that one of the samples was close to 3.9. This is all. But this is the characteristic of an estimator with an infinite variance. If I let it go, at some point, there's going to be a jump to 10. I'm 100% sure there's going to be a jump to 10. Maybe it will appear at 1 trillion samples, but there will be one. Okay, maybe it will be very hard to get a jump out. It will be very rare, but it's probably certain, yes.
Let's say that we do not know that we're on the wrong path. And we think that this, it converges at 0.9 or whatever.
Yeah.
If we keep going and we see a jump, is that the way to tell us we're doing something wrong?
Yeah, this is an excellent question. And the honest answer is that I do not know if this is true. So the question is, if I run my Monte Carlo estimate, if I haven't done anything, I haven't calculated, I haven't thought about the variance, whether or not the variance is finite. And I do my simulation and I see a jump like that. Is this an indication that I may have an infinite variance? I would say yes, but I don't have a proof for that. I'm going to have to look this up. But my suspicion is that if you see jumps like that, then yes, you are right. But the problem is that in a real application, you will not see them. You will see this. And that may look okay. I mean, okay, for 10,000 samples, maybe it will not look okay. But if you look, at 10,000 samples, it is very probable that you will not see a huge jump. Now, if you keep going, you will see a big jump. So I think is there a way to know that the variance of the estimator is finite? Probably no. I mean, from a practical perspective, be absolutely sure that it is not finite? Probably no. But is there things that may make you suspicious that you have an infinite variance? Yes, but you will have to, if you're calculating something with Monte Carlo, you're going to have to do it a few times and not just once. All right, so you should not really do Monte Carlo one time because that may give you something that's garbage. Now, one may argue that for a physical problem, a problem that has physical quantities, that comes from well-behaving physics-based equations, that will not blow up. It will not give you expectations or variances that are infinite. But for that also I'm not sure. Okay, so the answer is probably unknowable. Okay, but it is certainly possible. Yes.
Are you saying that, like, using a physical example, you know that your data points or your set of x is going to be bounded at some point?
So the problem is guaranteeing that this thing is not infinity, this expectation. And that expectation, by the way, could be infinity even if your q is just p. Even for p, it could be infinity. Now, what I'm saying is that you are the problem of figuring out if this is infinity or not. Okay, actually, I have a way. Yeah. So here's what you should do. You should estimate the variance using Monte Carlo, and you should see it growing. All right? I'll come back next time. I'll show you an example where this is probably the case. My suspicion is that the estimator for the variance will keep going up, no matter what. It will just go up as n goes to infinity. Whereas the estimator in the previous cases where the variance was finite, it would converge as well. Okay? I think this is the key. This is excellent questions. I should have thought about them, but obviously, you can't think of everything. Thank you. Next semester we'll teach it. Yes.
Why are we not talking about the second term for the variance equation?
Oh, because this is the expectation you want to calculate, and I'm assuming it's finite. Otherwise, you will also see it. I mean, as you try to estimate it, you will see it increasing if it is infinite. Right? So this is the original expectation. Expectation with respect to q goes away. It's the expectation you want to find. So that's probably the reason you want to find it is because you expect it is a finite number. Yes.
If the first term is finite, then the second term must be finite.
I don't think this is possible. Is it? Actually it is possible.
The integral of the positive function.
So what is the question? What if the first term is finite and this is infinite?
If the first term is finite, then the second term must be finite. Because
yes, this is true. This is true, because the square of that, right? So if the function is squared integrable, it is integrable. Is that true? Not necessarily.
The second term is less than the first term.
What was that?
The second term is less than the first term.
From the Cauchy-Schwarz inequality? Which inequality is that? Yeah, it is. It is less from Cauchy-Schwarz. But yeah, this is not our problem. Yes, if the variance is finite, then this expectation is definitely finite. But the problem appears when this is finite and this is infinite. Okay, then the MC estimator is garbage. All right, just to bring everybody on the same page, how can I know that if all I can do is Monte Carlo and I cannot really do this integral? You keep track of a Monte Carlo estimate of the variance and you should see it growing. If you see it growing, throw it away, go for a coffee, you need to think about it. All right? Okay, now let's go to the next step. which you would expect it, cures the previous problem, but it doesn't really do that. It's just another topic, okay? So we just go to another topic. We just show you some other kind of random numbers that behaves a little bit better than Monte Carlo, but there's a catch. We said that Monte Carlo's convergence is independent of the dimension, and this is absolutely true. Anything else really does depend on the dimensionality of the space. So you will see Latin hypercubes beating Monte Carlo for the examples that I'm going to show you. And actually up to moderate dimensions, they always beat Monte Carlo. But if you keep increasing the dimension, Monte Carlo will win. Okay? Because there is a moderate dependence of these methodologies on the dimension. And this will be true of all our UQ methodologies. So we will always find a UQ method. You will see later on polynomial chaos and more advanced techniques much later. So this will always do better than Monte Carlo in the examples that we see in class. But then if you start increasing the dimensionality of the problems, Monte Carlo will win. And there's no way around that problem. I mean, Monte Carlo always wins because it doesn't depend on the dimension. Okay? But for practical problems, when you have an actual, specific problem, you can construct a method that is faster than Monte Carlo. Okay? But you need to use your brain. Anyway, I'll show you Latin hypercubes. So Latin hypercubes give you random numbers kind of uniformly distributed. Okay? So they will give you, for example, in 2 dimensions, they will give you random numbers between 0 and 1. But they don't give you these numbers one by one. They give you these numbers in batches. So you're like, give me 5 random numbers distributed in 0, 1 square. Okay? And they have the specific properties. The following property. They take, if you ask them for 1, 2, 3, 4, how many are these? 5 numbers, okay? What they do is they take 0, 1, they split it into a grid of 5 by 5, and then they randomly pick a row, and they randomly pick a column, okay? And they assign a number there. And then the next number they pick, they also randomly pick a row, but it has to be a row that they haven't picked before, and they also randomly pick a column, but it has to be a column that they haven't picked before. This is how it goes, right? So you see that there is only one sample on each row, and there is only one sample on each column. This is the characteristic. And it is exactly because, it is because they spread the samples in this way, they get better properties than Monte Carlo when it comes to the variance. The variance is actually smaller for this. When you build Monte Carlo estimators based on these kinds of samples, you will get a smaller variance. But the very fact that they have to build this grid makes them dependent on the dimension. And at some point they will lose to Monte Carlo. So here's another example, right? So if you try to sample another set of 5 numbers, you just pick different rows and different columns. And these are 4 or 5 different Latin hypercube samples. Each color it's a different set of 5 numbers. So these are Latin hypercube samples, probably like 100 points. So imagine that to pick these samples, the algorithm splits the unit square into a 100 by 100 grid, and then for each sample it randomly picks a row and a column, and then for the next sample it picks randomly a column and a row that it hasn't picked before, and so on and so forth. What was that?
Is it uniformly distributed?
It is not uniformly distributed on the unit square, it is kind of uniformly distributed on the unit square. Okay? It looks like it is almost uniformly distributed.
They're not independent.
They're not independent, no. But they're kind of independent. Okay? They're independent enough, let's say. You will see what happens. So this is the difference. Look at the Latin hypercube samples, okay? These are 100 Lightning Hypercube samples, and these are 100 uniform samples. Do you see any difference? Look at them again. Lightning Hypercube samples, uniform samples. Lightning Hypercube samples, uniform samples. Do you see the difference? One is green and blue, and also the points are different, right? Obviously. So what happens with okay, so oops. I'll show you what happens. So in the Latin Hypercube samples, you can only get you may get samples that are close together, right? So like this and that and that. So you get samples that are close together, but you only get samples that, but you cannot get samples that belong to the same box, because on the background, the unit square is split into 100 by 100 boxes, and you can only get one sample per box. So there's a limit on how close together they can come. And it's very unlikely that you will find more than two of these together, but you will never find them inside each other's box. But with uniform sampling, you will always find things like that. Here you have 4 samples struggling to be the same region. You have clusters of samples. You have another one. You have another one here. And also the space is not covered so well. Okay, this is the only difference, basically. Anyway, I don't even remember why I had this particular figure. I don't. Yes.
So the point is going to end up being at the middle of the sample.
Yes, it is always at the middle. Yeah.
So just it's up to you to make as small as you want the square.
Yes. And pick you tell the algorithm, give me 5 points. It splits the square in a 5 by 5 grid, and it gives you the center. This is called centered Latin Hypercube designs. There are random Latin Hypercube designs where it picks the square, and then inside the square it picks randomly.
So if we make the squares very, very small, then we make it possible to have like overlap.
No, you're never gonna have overlapping, because they will never be on the same square. They can be on neighboring squares, but not on the same. It's impossible to get 2 samples on the same square.
Yeah, but if you zoom out, you're gonna see.
They will look like, yes. But the difference is that if you use uniform sampling, there will be clusters of points very close together, much more often. And also empty space. Of course, if you sample a lot, there will be no empty space. Okay? But you will see what I mean when we do the... Yeah, okay, so here's another way to look at it. So 2 sets of Latin Hypercube samples, green and blue, and you see how they are distributed. Compare them to Monte Carlo samples. So again, 5 with uniform samples. 5 uniform samples. In the red case, they only sample the left part. They completely ignore the right part. There's a lot of empty space always. The purple thing basically just samples the diagonal. Alright? So if you can afford 10,000 samples of whatever you're doing, fine, do uniform. If you have to do 5, you should probably do a Latin Hypercube design. Yes?
So if the goal is to get the points to be spread out over the parameter phase, then why not just actually like pick a geometry that is spread out instead of randomly choosing?
Because if you pick a geometry that is spread out and you do that every single time, you may get fooled by whatever function you have. So if, for example, let's say this is a real experiment, okay? And X and Y are the conditions of your experiment. And you can afford to do it 10 times. It is better to do 2 times Latin Hypercube designs than it is to split it, to put equidistant points. Because it will be as spread out as possible, and because of the randomness, it will not be fooled by weird things. So if you have a fixed design, and you decide that a priori, and let's say that your design is like this, okay? And then what if something happens there? You're not going to see it. What if something happens there? You're not going to see it, right? But if you randomize your samples, the design a little bit, you decrease the chance of missing something, okay? And also, you can do this design once. If you can do another set of 5 experiments, are you going to do the same thing? You're going to have to pick another one, okay? You're going to say, yeah, I will pick one by hand again. Another 5, like that. But then you're basically doing Latin hypercube design, right? All right. Let's see this applied to Monte Carlo. Okay, and we'll introduce an uncertainty propagation problem, and this is it. Very simple. It is a differential equation, right? We have dy dt equals minus a y. Okay, and that a is this thing, so it's exponential decay. Yes, it is exponential decay. And the decay parameter, I'm going to pick it to be random. Okay? Unknown, basically. So it's 0.1 times x1, where that x1 is a uniform number. So we have a little bit of parametric uncertainty for that particular model. And I also have initial condition uncertainty, right? So y0 is 8 plus 2 times a random number. Right, so there is a little bit of uncertainty about where we start. And of course, I scaled all the parameters so that I can use uniform numbers for the uncertainty. And this is how samples from this dynamical, it's not even dynamical system, from this ODE look like. So here I sample parameters, I sample initial conditions, and I solve the PDE. And I get one line, the ODE. I sample parameters and initial conditions, I solve the ODE, and I get another line. And it's always, I know it's exponential decay, okay, but the decay is always different, and the initial point is always different. But this is how they look like. Now the problem in uncertainty propagation most of the time is to find things like the expectation of your response as a function of time. Okay, so let me just write this down here. So this is the expectation of the response as a function of time. But if you look at the details, right, your response doesn't just depend on the time, it depends on these two parameters, x1 and x2, right? And this is what we're integrating over. We're integrating over these two parameters. So we're basically calculating this integral. x1, x2, probability of x1 and x2, dx1, dx2. But of course, we have picked these guys to be uniform numbers, so that p, x1, x2 is just 1, and you're integrating. Come on. It disappeared, okay? But let me write it again. So this integral is really this integral, 0 to 1, 0 to 1, yt, x1, x2, dx1, dx2. And the only problem is that this term right here comes from solving your ODE. So for 1x1 and 1x2, you need to run a Runge-Kutta scheme, for example, to solve your ODE, or an Euler scheme to solve your ODE. Okay? And this is the integral that you see here. So one thing that you may be interested in is this, because this is going to give you your expectation about, what is going to happen if you don't know the decay rate and if you don't know the initial condition. And the other thing that you may be interested in is this, which is the variance. Right? So the variance is this, the variance, let me use red. So the variance of yt is basically the expectation of yt x1, x2 minus the expectation of yt, which is what we had before, squared. Okay, and you can work out what integral it is, but it is also an integral with respect to dx1 and dx2. Okay, and this integral gives you an estimate of how uncertain you should be about the response as a function of time. And you see that uncertainty for the exponential decay grows at you have a finite uncertainty at the beginning because you don't know the initial condition, and then it grows, the uncertainty grows, but eventually for exponential decay, it will become zero because you know it's exponential decay, and at big times it will converge to zero. Right? So you expect if you continue t, you will get the variance go to zero. Okay? And you can get, of course, get lower and upper error bars. So this would be now, this is the mean or the median. I think I do the median here. The 50% quantile. This is the 2.5% quantile and the 97.5% quantile. And this bounds, what is going to happen with 95% probability. And you can show more things. For example, you can show intermediate quantiles if you want, right, to get a better visualization of the uncertainty. Actually, how to visualize uncertainty is a new field, very exciting field. Because, okay, this is one deep problem, right? It's not a big deal to visualize uncertainty, but how do you visualize uncertainty when you're solving PDEs in a six-dimensional space? Okay? Yes. Okay. Now for this particular problem, again, the reason I picked it is because I can solve for the expectation and the variance. Okay. And it is exponential decay, so I can just solve the ODE and I'm going to get that expression over there so that I can just analytically integrate this expression over x1 and x2 to get the expectation as the expectation as a function of t and the variance as a function of t. All right? So I can compare to them. So now see what happens. See what we did. We estimated the variance as a function of time in three ways. The blue is the analytic estimate, which for a real problem you won't have. And then we constructed an estimate using 10,000 Monte Carlo samples, which is the green line, okay, the green dashed line. And we also constructed an estimate with 10,000 Latin hypercube samples. So the x1 and x2 are sampled from Latin hypercube. And that will give you the red line. So just visually, you see that 10,000 Latin hypercube samples give you a better estimate than 10,000 Monte Carlo samples. And that is true for moderate dimensions. So you go up to 50 dimensions, maybe even 100 dimensions, Latin hypercube will beat Monte Carlo. As you start increasing your dimensions, Monte Carlo will beat Latin hypercubes. Okay? But for small dimensions, 5, 6, Latin hypercube always wins. And I will demonstrate right now how much it wins. LHS, Latin hypercube sampling.
And now the x.
X-axis, time. So this is time, and this is the variance of the response as a function of time. Right? And you see three different estimates. Blue line, analytic estimate. Green line, Monte Carlo estimate. Red line, Latin hypercube sampling estimate.
What time is it? The number of samples.
I think it's around, no. There's no number of samples here. The time is the time of the physical problem. Okay, this time. Yes.
Between MC and LHS, is one of them easier to construct as a?
They're both ridiculously easy to use.
Why?
It's they are the easiest unset propagation methodologies that you can use. It's the first, it's the where you should start, unless you have something that you cannot sample. So if you have a computer code that takes a day, probably you need to think about it a little bit before you start. If you have an experiment that is expensive, you need to think about it as well. But if you have something that takes a minute, less than a minute, 5 minutes even, then you can just sample it to death.
Why are they both smaller than the true variance?
This is just accidental. They could be bigger than true variance.
You divide it by the n, the number of samples, so n minus 1.
So it doesn't really matter, okay? You could get, if you wanted to use an unbiased estimate, you would divide by n minus 1, and you can construct an unbiased estimate. But for 10,000 samples, doesn't matter, okay? Doesn't matter to the point that it just doesn't matter. And the way you construct these estimates, we construct this estimate is by averaging x squared and subtracting from it the square of the estimate for the expectation. So it's definitely a biased estimate, but doesn't matter.
Why don't you use the unbiased one?
Because it's a pain in the ass to type it. And it will give me the same result for 10,000 samples. Seriously, that's the reason. It does. So the unbiased one, it's not better than the biased one for big N, and it's debatable even if it is better for finite N, very small N. It is also you can have a unbiased estimator with a huge variance that is worse for finite N than a biased estimator with smaller variance. So I would suggest not to worry about that at all. If I was worried, I would have introduced the estimator. If you notice, all my estimators are 1/n average, okay? Sometimes this is unbiased. Some other times, like for the variance, it is biased, but we don't care, okay?
So here you mean the dimensions of the stochasticity when you say the like Monte Carlo works better if you have higher dimensions.
So now I'm talking about the random variables, which here are x2 and x1.
So the dimensions of the random.
Yes. If you have two x's, two random things, then Latin hypercube is better. If you have hundreds of x's, thousands of x's, then Monte Carlo will probably be better. And when that happens, we cannot really predict it. Anyway, so here's let's do a little bit of convergence analysis. All right. So what do I mean by that? So for a fixed number of samples, there is actually a typo here. I should not have a T. Actually, no. This was correct. All right. So the numerical solver for the differential equation gives us the solution of the differential equation at different points in time. So let's call these times t1, t2 up to t and t. And I have about 100 or 200 such points in time. Now for each one of these points in time, we can get the true variance, which is the analytical variance, and we can compare it to the estimated variance. With an unbiased or a biased estimate, it wouldn't really make any difference. Okay? So here, that estimated variance could be the Monte Carlo estimate of the variance using uniform samples, or the Monte Carlo estimate of the variance using Latin hypercube samples. Now you compare the two, you square the difference, okay, and you sum the difference for all the times, and this is an estimate of how wrong you are. All right, so this is an estimate of the that's not even said, okay? It's an estimate of the error. You can see it's a square difference, sum of the square differences. Yes?
So how do you deal with a problem for which analytical variance is not possible?
You cannot get this estimate, obviously, right? So for a problem where you cannot get this, you're gonna have to construct an epistemic error bar for the variance, just like we constructed previously for any Monte Carlo estimate. Okay, and it is possible to construct an epistemic error bar for the variance. This is just, I mean, what I'm gonna do now is I'm gonna use this, which is of course something that you cannot have in reality, to show you that Latin hypercube designs beat Monte Carlo. That will give you a smaller root square error as a function of the number of samples. Okay, this is what I'm gonna show you. In reality, you cannot have that. The only people that use this error in practice are people like me who develop uncertain quantification techniques and they want to show that they're better than other people's techniques. Okay, so you have to use a problem in which you know the solution, right? But in practice, you cannot do this, the plot I'm going to do right now. All right, so here's just one realization of what can happen, right? So you just go and start sampling with uniform samples and estimate the variance and compute the root square error and see how it's going to go down as a function of samples. So here you have number of samples. The blue is the error in the estimate of the variance from Monte Carlo, and the green is the error of the estimate in the variance estimate of Latin hypercube designs. Okay, so you see that Latin hypercube does much better if you do it once, but these are random things, so perhaps you want to do it a few times. So if you do it 100 times, I think here we did it like 10 times, not even 100 times. If you do it 10 times, you're going to get 10 different answers. So the truth should be the rate of convergence. You can see it from not the rate of convergence. You can see the robustness of each one of the methods as you increase the number of samples. So you see that Monte Carlo actually gives you, on average, it gives you a root square error that goes down like that. Okay, but the 10 estimates were within these bounds. So meaning that if you run Monte Carlo 10 times, the error will go down like that, but the real estimate could be anywhere in here. Now, the Latin hypercube seems to go down faster at the beginning, and the bounds inside which the error is are also smaller. Right? So for the same number of samples, you can trust the Latin hypercube estimate more than you can trust the Monte Carlo estimate. But if somebody asks you, does Monte Carlo with uniform samples converge faster or slower than Latin hypercube with uniform samples? You cannot say that Latin hypercube is faster. Because if you look at the rate, if you look at the slope of the curves, they look very similar. The slopes look very similar. They're both 1/square root of n, the slopes. Right? So it's not that this converges faster than that. They converge at the same rate. It's that this has a smaller epistemic uncertainty. This is what is the difference.
Is it for smooth functions only?
This is for any function that has finite variance.
Yeah, but if the function isn't smooth, then is the LHS still better than MC?
Yeah, I think so. Yeah, it will be better. As soon as the square of the function, I'm actually 100% sure. As soon as the function is square integrable, Latin hypercube design in small dimensions will beat Monte Carlo because the estimator has a smaller variance. So if you want to do the math, you compute the epistemic variance of the Monte Carlo estimator and you compare it to the epistemic variance of the Latin hypercube estimator, and the epistemic variance of the Latin hypercube estimator will always be smaller for low dimensions. Okay?
So other than that, so we can see that with lesser number of samples we can achieve the variance error to be lower for Latin hypercube sampling.
Yes.
Is that in this case or all the cases?
This is the so Latin hypercube beats Monte Carlo in all things that you would like to estimate if you have a few random variables, and by a few I mean anything between 1 and 100 or even more. Okay, but for as you increase the number of random variables, Monte Carlo will win. So for example, if you want to propagate 5 or 10 or 50 uncertain parameters through a simulation, Latin hypercube will win. If you want to do molecular dynamics, Monte Carlo will win.
So my question was like, can we achieve, so when LHS is better than Monte Carlo, we can achieve better results with lesser number of samples?
Yes, 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 yes. So if you know, so here you see the true error. Okay, so this is the true error, how the true error goes down. Even if you compute the epistemic variance of your estimate, which is what we derived the last time with the central limit theorem and so on, if you compute it with a running average, the epistemic variance for the Latin hypercube designs will be smaller than the epistemic variance for the Monte Carlo. So you will know that you're doing better.
In what situation is the Monte Carlo better?
When the dimensionality of the problem increases. Because here's what happens. The convergence rate of Monte Carlo does not depend on the dimension of the problem. But the way we sample from Latin hypercubes does depend on the dimension of the problem, because we'll have to build this grid in d dimensions and pick a box, right? So at some point, you're not going to be able to do that. You can't do that in like a billion dimensions, right? So Monte Carlo will beat you. Will beat you because it will be impractical to construct the grid and do the sampling. Yes.
No, Professor, as you increase the dimensionality, doesn't the computation becomes more expensive too?
Yes.
So in that case, like, it wouldn't make sense to use Monte Carlo right away.
So here's the problem. When you increase the dimension and you want to do statistics or probability, all the methods will fail. Okay? But Monte Carlo will be first, for the winner. Okay? Everything else will fail before Monte Carlo. Everything else will fail spectacularly. You will get full memory is full errors. It will get your computation will finish when the sun will blow up. Kind of errors, okay? But Monte Carlo, so you will not be able to compute anything. But Monte Carlo, you can at least take a few samples and do the average, okay? No matter what, no matter how big the dimensionality is, because generating the Monte Carlo sample does not depend on the dimensionality that heavily, and then the convergence rate does not depend on the dimensionality as well. And the implementation is ridiculous. Just sampling random numbers, plugging them in your model, and is also parallelizable in an embarrassing way. You just have 5 computers, fine. Sample 5 things simultaneously, right? And that's why nothing will beat it. Now, if you have a truly difficult, if you're telling me that I have a problem that has 1 million random numbers and 1 million uncertain parameters, and it takes about 1 month to run a simulation, then perhaps you are not ready to do uncertainty quantification in this problem, right? So perhaps you need to do a little bit of math to simplify it, do some experiments and eliminate some of the parameters. Think about it, basically. before you start doing anything, right? So right now, let's say it depends what kind of UQ can we do. Molecular dynamics is essentially UQ because you're doing Monte Carlo. So we can simulate things that are a few nanometers, but it takes a while, and you can only do it a handful of times. These are really high dimensional uncertainties. But they rely on the evaluation of the energy, molecular energy, which takes like that to do. Okay, we just do it a lot of times. That's why they are expensive. If you want to do more serious things based on simulations that you have developed over the course of 5 or 10 years in your group, right? The limit right now, I mean, you're limited by your computational power, and realistically speaking, if you want to use a supercomputing cluster, I think the limit would be 10 to 20 parameters if your code runs in, let's say, a day, okay? And you can afford to run it for like a month. But again, you can run it faster, you can do more on certain parameters. You can run it, you have a more expensive code, well, you have to do less parameters. Yeah, I mean, we have finite resources, we cannot do everything. I hope this message is passed and well understood. But anyway, this is the kind of problems you want to have. Because this is, if you can just do something, let the industry people do it. Okay, so you want to be in the regime where things cannot be done. At least this is my opinion, right? Unless you want to start a company, then you probably want to be in the regime where you can actually do it. But anyway, so let's spend 3 minutes to talk about this further. Yes?
What's the dimension here?
2. So in the example, the previous time, the dimension was 1,000, and it still worked with Monte Carlo. Now, in the previous example where we had thermal conductivity to be uncertain. Now, when we're gonna go to polynomial chaos next week, and a 1,000 dimensional problem is going to be, I mean, we cannot even start to talk about it. Okay? I will explain why, but it cannot happen. You can only do that kind of problem with Monte Carlo. What else? Yeah, alright, so there's a new homework on Gaussian processes. It is only examples, numerical examples, okay? You will familiarize yourself with doing regression, and hopefully you will understand how to pick the covariance function of a Gaussian process and what it means. This is due Thursday. There's not going to be an extension. If you started Thursday afternoon, you will probably not make it. So start a little bit earlier, okay? You don't have to start today. It's probably okay. But you're going to have to start Tuesday at the worst case scenario, okay?